Well, thank you. Thanks for the introduction. Thank you for inviting me. It's always nice to yes. Thanks in general. There are many words here: the pure mapping class group, character variety, and there are different types of players in the game. So I will be carefully defining what they are, and we'll see what are the results and so on. So let's start with saying what is a character variety. So in order to understand that, we start with, first of all, okay, so we start with what is a representation variety. So if I give you, and because I want to focus on this, I will limit myself to only character variety of the fundamental group of a surface. So in this talk, sigma sub g comma n is always a surface of genus G with n-punctures. And here is a shape of a surface of genus G with n-punctures. So this one's there. So usually people draw surfaces like that, but I don't like it as much because it's kind of deceiving. You think that this one is different from the other one because it is in the middle, but it's not. So it's better to think about it like a sphere, and then you're attaching handles to them. So this way you see that they are all the same. And then what is the fundamental group? The fundamental group is generated by, so again, because of the symmetry, it's rather easier. I just draw for one of the handles, and then you just rotate them. So you go like these curves. And then you look at the rotated version for each one. And then you go around each one of the handles. And you come back. And then you can also go around the punctures. So you get these shapes. And now, so the way that I have chosen the orientation, you get this type of relation that if you go the commutator of the yellow and red, then you get a necklace for the first handle, And then you do the same, you get the necklace for all the handles, and then you glue them together, and then you can glue them together with a glue, and then contract it from the back of the sphere. So that way you get this relation. So, but in order to be actually correct and get the commutator as I promised, you have to take the inverse of V1. So it's slightly different from the relation that we often present for the fundamental group because of these inverses. But I chose those for a particular reason. The point being that if you start with this ordered set of generators, and you take a word which is given by this order and go one after another, you get a simple curve. So for instance, if I go A1, A2, because of the orientation that I picked, you get a simple curve. So this orientation that's why it's referred to this type of generating set. It's called an optimized set of generators. And you can understand them by looking at a small neighborhood of your base and following the arrows. So the arrows can kind of tell you if you are an optimized set of generators or not. I will come back to this, why this is important to have these things as simple paths.
What's the advantage of taking B1 inverse and not B1?
So the advantage is that if I give you a word, so let's say I choose S1, S2, the scale from the set of generators, but in an ordered way, then this can be represented by a simple curve. So the orientation helps me to get simple curve. So if it was the other way around, then it would not be simple. So it would cross itself. Okay, but so in particular, the fundamental group of this is isomorphic to, and I'm going to fix this presentation as my group. So it's isomorphic to generators given by A1, B1, AG, BG, C1, Cn, and that is the only relation that we have. Okay, so now we are interested in understanding representations of this into it is SL2. So I give you a ring, and I'm interested in understanding what are the possible representations of this group into SL2. And let's put it in a fancy word and think about it as a functor. So R sub G comma N is a functor from the category of rings, unit of commutative rings to the category of sets. And again, what is it? I give you a ring. It spells out the possible homomorphisms from this group to SL2 on. Okay, but if you want to understand it rather concretely, so this means what? This means I have to tell you 2G plus N 2 by 2 matrices that satisfy this relation. So it boils down to an algebraic relation. So that means I can view this. So this can be viewed as a closed subscheme of SL2 raised to power 2G plus N as a Z scheme. So it's a closed subscheme. Of this. Okay, so now in practice, we are often interested not on representations, but representations up to conjugation of SL2. What do I mean by that? So we are kind of interested in the surface at the end of the day, but here it's about surface with a marked point. If I change the marked point, I'm going to lose the fundamental group. So it's not quite natural to talk about this if you are interested on the surface. But if you change the base point, it's kind of changing your representation up to conjugation. So then it's better, it's more natural if you are interested on the surface to talk about these representations up to conjugations. So you want to model by an action of SL2 here. Okay, but it cannot, in general, it's not easy to model the scheme by a group. You don't necessarily get a nice structure. But let's try to think about it. So it means that what is clear is that the traces will be invariant under the conjugation. So how Friquet started working on that, and then later Horowitz made it more clear. He said, okay, so let's try to do this. To any element of my group, let's attach a variable, T sub gamma, which is supposed to track the trace of this matrix. But at the moment, we are not thinking about the matrix. I'm just assigning some variable. So I'm looking at the infinitely generated ring, T sub gamma, for any gamma inside my group here. I'm going to attach a variable T sub gamma. And then I'm going to model with it by the trivial relations that we would expect to get. What do I mean by the trivial relations? If I give you two matrices, 2 by 2 matrices, so if A and B are 2 by 2 matrices, no matter what ring, then the Cayley-Hamilton says that, so A squared minus trace of A times A plus identity 0. So from here I deduce, so one obvious relation is that trace of A squared plus 2 is supposed to be trace of A squared. That's at least one relation that I get for a single variable. The other relation that I get is by multiplying both sides of this by A inverse and then B, I get that AB plus A inverse B is the same as trace of A times B, and then I take the trace of both sides, and I get what's known as a pre-K relation. So this means that there are two obvious type of relations if I think about T sub gammas as traces. So one relation is, so I take gamma, these are all the variables. Then I model by the ideal generated by T sub, the relation that comes from here, T sub A squared minus T sub A squared minus 2 for every A inside my group. And the other relation is the one that comes from the other one. So TAB plus TAB inverse minus TA times TB for every A and B that comes from the group. So I look at this ring and I call this guy A of G comma N, because it only depends on G and N. So in the spirit of defining schemes, so this is supposed to be the coordinate functions of my scheme. What is not clear is why this is if it's not a finitely generated ring, then it's not going to be as interesting. The technical word means that we don't get a finite type scheme. But what Horowitz showed is that he showed that if I start with a generating set of my group, and these results, they do not have to be this particular group, it can be any finitely generated group. But if you start with a fixed generating set and take in increasing words, then those traces are enough to generate this ring. So Horowitz showed that this ring is generated by.
What time are we talking about? Which
1972.
70, yeah, 1970.
It's a student of Magnus at NYU.
That's right. So this is generated by T sub omegas.
Did he really work with any ring?
And yeah, this is what he worked.
He worked with an arbitrary ring?
I mean, this is what is a coordinate ring. Yeah. So then, yeah, he was interested in understanding this coordinate ring. Yeah. So by T sub gammas, such that T sub omegas, such that omega is S1 divided dot Sk, where these are increasing from the generating set. So then we are going to talk about the spec of this ring, and we are going to call that one the character variety, the SL2 character variety of the surface. So the character variety of the surface is the spec of this ring. Now we know it's finitely generated, which is a finite type. And kind of you can see it now. If I start with this representation variety by taking traces of the elements, I'm giving you the values of these coordinates. So therefore, we do have a morphism from the ring of coordinates of this guy to that guy by sending the variable T sub gamma to the trace of rho of gamma. So that means that we have a morphism from the representation variety to the character variety. Okay, so I prefer to think about it, to understand these better, I prefer to think about the R points of these schemes and describe them at the R points. And R points always means I'm describing them in terms of bunch of equations, and R points mean I give you a ring, you look at the solutions over there, and what does this map do? So at the level of R points, if rho is an R point here, then we know it's better to think about it as a group homomorphism from this group to SL2R. Then what this pi does is simply, so then I have to describe what this means, right? So how do I describe an R point here? By telling you how these coordinate functions are evaluated at that point. So then T sub gamma at this point is simply trace of rho applied to gamma. That is how you should think about what this pi is.
What's the crude dimension of this field? AGM?
So it is exactly what you should imagine. I mean, so after base change, when you go to complex numbers, that's exactly the dimension. Okay, so that's the crude dimension is exactly what we want. What do I mean by that? So in the representation variety, each one of them is a matrix in SL2. That means each one is contributing dimension 3, and you have 3 relations. So it becomes 2G plus n times 3 minus 3. And then when you go to the character variety, because you're modding out by SL2, you subtract another 3. That's exactly the dimension of the Teichmuller space. And there is a reason for it.
And the character variety, I suppose, is connected as a scheme.
Yes, because I mean, so by passing to, so as I described, there is a Zariski open subset here, which then this becomes actually a geometric quotient of that. So in particular, this one is irreducible, that one will be reduced. But what we will discuss some other irreducibility, which is going to be more important for us. But for now, let's point out one more thing in order to make this slightly more clear. So suppose that I give you a small case when G is 0 and n is 3. In that case, geometrically, people refer to this as pair of pans. So because it's a surface with 3 punctures. So it's a pair of pans, and in hyperbolic geometry, it is well known that if you want to describe hyperbolic structure on the pair of pans, it's enough to tell me what are the lengths of the geodesics at the boundary, which means that by knowing only the values at the boundary, it's enough. And it is consistent with what Horowitz is telling me. So Horowitz says that in this case, pi 0, 3 is generated only by 3 C1, C2, C3 with a single relation. So I can drop the last one and just take C1, C2 as the set of generators. And what Horowitz says that is that this ring is generated by T sub C1, T sub C2, and T sub C1, C2. Okay, and in fact, in this case, that's it. So there is no relation between them. So it's an affine space, and it is consistent with what we see in the Teichmuller space, that any values can be chosen as length of the boundary curve. By the way, length of boundary curve is essentially log of these in the Teichmuller space. So in this case, it's just an affine space of dimension 3, and so this means that the character variety in this case is just an affine space of dimension 3. And then if you do the same thing for genus 1 with 1 puncture, it's going to be the same. So in that case, so if I give you a torus, 1 puncture torus, so this one is generated by A, B, C, and the commutator times C is supposed to be 1. So again, it's generated only by A and B. So Horowitz tells me that this ring is generated by T sub A, T sub B, and T sub AB. And so that's it. And in fact, in this case, again, there is no other relation between them. And so this again becomes the affine space. It's isomorphic. The affine space in the 3 parameters. But one should not get fooled by these. So, as for instance, if I look at CH04, so if I look at this sphere with 4 punctures, Then again by Horowitz, this time we get, so this one, the pi 04. It's a free group generated by 3 elements, essentially C1, C2, C3. Because C4 is the inverse of these guys. And this time, this is not going to be, so if I look at the words, it becomes what? It is so it is generated by T sub C1. So now, as we will see later, the traces of the boundaries will be kind of constant for us because of the reason that I will explain. I'm interested in the action of the mapping class group, pure mapping class group, and these things will not change the trace at the boundary. So we kind of treat the T sub C1, T sub C2, T sub C3 as constants, but these things we do not have a control on. So I'm going to call them. So by Horowitz, I have to look at increasing words. That means T sub C1, T sub C2, T sub C2, C3. And because C1 is dropping, I am calling it X. T sub C1, C3, because C2 is dropping. T sub C1, C2, because C3 is dropping. And I have 4 other variables, T sub C1, T sub C2, T sub C3, and T sub the product of them. And remember, because the product is the same as C4 inverse, this thing is the same as these ones. After all, inverse of a matrix of this in 2 by 2 matrix have the same trace as itself when it is in SL2. So now, having that in mind, I know by Horowitz that this ring, so maybe I have to start with A. So this ring is generated by X, Y, Z, and these other variables that I said, you have to kind of think about them as constants, but there is a relation between them, and the relation is given by x squared plus y squared plus z squared. It should be equal to some linear combination of x and y and z, but linear in the coefficients that coming from these guys. Okay, so it should be some constant, some polynomial of t sub 1, t sub 2, t sub 3, t sub 4 times x. So the upshot is that not always you're going to get a fine space. So this is an example where you do have a, in fact, if you think about these as constants, a quadratic equation. Okay, so now we have some sort of an idea on what the character variety is, but not quite, right? Because I didn't quite give you the relation between the representation variety and the character variety. So let's try to connect them a little bit better. So for instance, if I give you the traces coming from character theory of finite groups, we would sometimes expect to see if we can understand the representation, at least whether or not it is absolutely irreducible. So meaning, do I have a subspace that is invariant under the action of my group or not? So let's think about this a little bit.
Alireza, why representations into SL2? What's
so again, it has something to do with the Teichmuller space. So as I will explain, when you look at the character variety, the real points of the character variety, then it's going to have 2 major components. So one of them is the SL2R components, and the other one, the unitary ones. So the SL2R is, if your representation is proper, it's going to give you a hyperbolic structure on your surface. So your Teichmuller space actually lives in the SL2R.
Answer is restricting to that. He could have looked at other groups and then it's called higher Teichmuller.
Absolutely. Absolutely. So that is also studied. But historically, it was studied for SL2 because of the connection with Teichmuller space. Right. So now, So again, if my representation actually is not absolutely irreducible, so if rho of this is not absolutely irreducible, this means that I can kind of upper triangularize it. And therefore, when I take the commutator of this one, the traces all become 2. So that means that if I pick 2 elements, the trace of the commutator should become 2. So it's kind of important to understand what is the trace of a commutator. And if you play with the Fricke relations, these are called Fricke relations, then you understand what is the trace of a commutator. So trace of the commutator is going to be trace of a squared, trace of b squared, trace of ab squared, minus trace of a, trace of b, trace of c, plus 4. Okay. Sorry, plus 2. Let me see if I want to send it minus 2. What is trace of AB, sorry. Thank you. So trace of the commutator is trace of A squared plus trace of B squared plus trace of AB squared minus the product of the traces minus 2. If you play with the relations, you end up getting this computation. So that means this equality is kind of asking for what we call discriminant of 2 elements, delta AB, which is equal to this thing minus 2. So that's why I had this minus 4 there. So we call this minus 4. That is what we call the discriminant of these 2 commutators. Okay, so now what I'm saying is that if my representation is not absolutely reducible, then all of these discriminants should vanish as I plug in them. So that means if I do want to get absolutely reducible, I have to avoid the divisors that I get out of this ideal. So that is what Salehi does in order to define the subspace of absolutely irreducible representations, and explains that you can detect it at the level of the character variety.
The -2 on the bottom line, because then the -2.
Absolutely, thank you. Thank you.
Not that it's important.
No, it is important. Okay, so then again, so as I said, we are going to look at the divisors of the ideal generated by all the discriminants as A and B vary inside the group, and then subtract it out. And so and then I'm going to decorate this to be the one that I had before minus the divisors of this. So let's call this guy the divisor. So minus d. And I look at the lift of that through the pi that I had, and I'm going to call that one the rep Gn price. So in particular, we end up getting the morphism from this Zariski open subset of the representation variety to this. So again, in order to understand this a bit better, I prefer to describe the R points of these schemes. So this is more or less due to Sato. For any unital commutative ring, so if I give you a rho belongs to this, precisely when the R span of the image is the entire 2x2 matrices. So now, on this, I gave you this description. How about this, and what is the relation between them? So for instance, let's start with saying, if I give you 2 points here, if they map to the same thing, then what happens? So let's say, and for simplicity, I'm going to denote, select bracket of a point to be the pi of that point. So then the proposition says that if I tell you the bracket of 2 points in the absolutely reducible part, rho 1 and rho 2 are here, and they are in the same, they go to the same point, then, so we would like to say that they are conjugate of each other. It is kind of true, but we need to enlarge our ring. So there exists some ring extension and some ring extension of S. It's quite restrictive, and I will explain it a bit more. But it's not okay. So there is some ring extension and some matrix X inside GL2S, such that conjugation by X goes from one to another. So this ring extension is kind of restrictive. For instance, if R is a unital is UFT, or if it is if every projective finitely generated projective module is local, is free, then it's going to be again the same ring. So the same as, so the special case would be if R is a UFT or a local ring, then I can choose, S can be chosen to be R. So in many cases that are of interest, we can conjugate it within the same ring and get the other point. But so far I have described kind of going from here to there. What happens if I start with an R point here? Do I have a lift? Can I realize? So that means I'm giving you a bunch of numbers that have the potential of being traces of some representation. Can I find a representation whose traces are these numbers? So, as I have mentioned, historically, people studied the R points of these character varieties. And in the case of R points, we know that there are kind of two regimes. So if I look at the R points of this,
Real.
the real.
It's a bit
You're overworking.
R is an arbitrary.
Okay, so, yeah, but this R is the real.
We can thank Don Knuth for that.
Yeah, so this one either is coming from representations that are real, so the row is in the real points, or of course I can take a unitary representation, and then traces of a unitary representation is always real numbers. So I pick a row from, so bracket of row, such that row from I the unitary matrices, as long as it is absolutely reducible. So it was known that even in the case of real, I cannot understand the traces within the real number. I need to go to complex numbers in order to realize them as traces of some representation. And the result in general is kind of the same flavor that if I give you a point inside the character variety, not any point, it should be inside this guy, otherwise you cannot realize it. But if it is on this Zariski open part for any ring R, then there exists a faithfully flat extension. So nice, rather nice, but not exactly. And I will give a better understanding of this when R is more special, and a representation. Inside this ring, such that the traces are giving me the point X. Now, if the ring is, the ring R is a bit nicer, and I'm interested in the case that I can, at least the p-adic numbers is the ring that I'm interested in, p-adic integers. So if D is a compact DVR, like p-adic integers, discrete valuation ring, then you don't need to go to larger ring. Then you can already realize it within D. So then there exists a representation to SL2R such that this goes to X. So this kind of boils down, the proof boils down to two steps. For finite fields, it was a rather known result, but it goes back to the 70s. And then you need a Hensel type argument to say that you can extend it to mod whatever power of the maximal ideal that this thing has. And the compactness helps you to write it as a limit. So it's enough to understand it for each lift.
What
and do the
happens
Hensel.
over Z? What happens if I?
Over Z, yeah, so we don't know. Yeah, I mean, it's kind of like, so the Markov triple, as I mentioned it, is one type of question that can appear and Markov tried to answer it, which is for one puncture torus. Special type. In general, it's not, so for even for Z, so you do need the ring extension, and I don't know.
I need to understand this space fully flat, or can I ignore this?
You can ignore it because for the purpose of my talk, I want to apply it for DVRs.
One other question. So these propositions deal with, naive pre-images. So what do you know about the fibers of this morphism?
So as I said, in fact, this statement over here tells you that this quotient is a categorical geometric quotient.
I see.
So this statement over here tells you that. Okay, so, but I mean, what I'm interested in, and if one gets out of this proposition, this picture we are going to use is the following, that if I take the rep G comma n cross D, then I have a map going here. And if I take an ideal of this ring, I can mod out by that ideal. And I can do the same by modding out the representation that I have. And then look at the traces. And this statement over here allows me to show that all these maps are surjective, assuming that these compact DVR. So all these maps are surjective. So again, let's try to think about it. It means if I give you a bunch of numbers that have the potential of being traces mod A, then you have a representation over D that mod A, the traces gives you those. So this by itself is a non-trivial statement. Okay. So even at this stage, let's say I give you a representation mod P to the K, then it comes from a representation of p-adic, right? So it gives you some information about the representation. Okay. And in this picture, we also know what are the findings. So because of the earlier result, we know that every fiber over here is a single GL2D orbit. Because we know if two things go to the same thing, they are conjugate of each other within the same thing because D is a local ring.
This is a very stupid question. At some point, you're going to use the mapping class to.
So now I'm done with this. I want to describe what is mapping class.
It's getting very
Outside of mapping.
This is
seminal
algebraic dynamics.
That's correct. So far, no mapping class group. Now I want to define mapping class group.
You fit into the seminar. It's called groups and dynamics.
Yes.
Okay.
Okay, so now here is the, so now I've defined what is the character variety. Now, then the next mysterious word is what is the mapping class group? So mapping class group of any manifold in particular surfaces is any differentiable manifold is the group of diffeomorphisms modulo homotopy. So rather I can say I'm looking at diffeomorphisms of my surface, orientation preserving diffeomorphisms of my surface, but modulo the connected component of these. So the ones that are connected to the identity, I'm modding out by that. So I'm not interested in diffeomorphisms that you can deform one to get to another. So I'm modding out by the connected component. That is called the mapping class group of the surface. So in particular, okay, so let's try to understand them a little bit. An important example is like this. So I pick a simple curve inside my surface, and then I cut out the neighborhood of that simple curve, and then I twist, let's say, the left side 360 degrees, and then glue it back. So this is a diffeomorphism of my surface. So it gives me a class inside the mapping class group. This guy, and because it's a class, it doesn't depend on what neighborhood I've chosen. So I can shrink it, I get the same class. So that element is called the then twist. So for instance, what it does to this particular curve is just twist this above that. So I start with this, twisting it, and then I get a new curve. So it's called the then twist. And what is known is that, okay, so now that's one part. The other part is when I give you a diffeomorphism, I'm just permuting the punctures at the end of it. By passing to a subgroup, a normal subgroup, I can fix all of them. And that subgroup is called the pure mapping class group. So the pure mapping class group fixes all the punctures. So that's the definition of pure mapping class group. Now, so the pure mapping class group fixes the punctures. But I put it here and I have to clarify what I mean by that. I mean, the diffeomorphism should fix the punctures, but I'll come back to understand it a little bit better. So there is a result by Sukresh that says that in fact then twists generate all the pure mapping class groups. And then people try to find the minimum number of then twists that can generate the pure mapping class group. And Humphreys showed that if genus is positive, then you only need these generators to generate it. So the yellow ones, the blue ones that kind of glue the handles together, and only two of these reds, you don't need all the way. And then the green ones that kind of separates the punctures from each other. So you only need these if G is positive, and if G is 0, that means if I give you a sphere with a bunch of punctures, then you take a subset of that, take a curve around it, take a then twist about those. So take any subset that has at least two elements in them, and then do the then twist about those. And those generate the pure mapping class group, which is essentially, I mean, they are related to the braid group, but we don't mind. I mean, we don't care about that. So the pure mapping class groups are generated by these when genus is 0, and those are called the Humphreys generators. Okay, now, but let's make it more algebraic. So if it's diffeomorphism, we don't like it much. In fact, again, if I give you a homeomorphism or diffeomorphism of the surface, if it was a marked diffeomorphism, this means that if I fix the base point of my fundamental group, then it was clear that I'm getting an automorphism of the fundamental group by just following what it does to a curve that's based at that. But when I give you an arbitrary diffeomorphism, the base might move somewhere else. So it's not going to give me an automorphism, it's going to give me an outer automorphism. So there is always a nice map from the mapping class group to the group of outer automorphisms of the group. And what Dan, Nielsen, and Baer showed it showed that the mapping class group is isomorphic to that part of the, so maybe the pure mapping class group. I'm going to denote the pure mapping class group by gamma sub G comma n. So this is isomorphic to those outer automorphisms that preserve the conjugacy classes of the boundary curves. So outer automorphisms always act on the set of conjugacy classes of a group. And now we want to fix the conjugacy classes of the boundary curves. So we fix this presentation, and I have to fix the conjugacy classes of that. And the map that I have said, the Danielson Bear says that this pure mapping class group is in fact that. I can identify with this. And because it's often the outer automorphisms is not that easy to work with, we want to work with a subgroup of the automorphisms. So I'm going to call that one to be pure automorphism. So I'm going to. So it is slight. So the pure automorphisms of this group, but then I have to also kind of tell you the C1 through Cn. Because this is at the end of the day a free group, but this particular pure automorphisms mean you remember what the CIs are. And then these are the set of automorphisms of this free group such that theta tilde of conjugacy class of CI goes to the conjugacy class of CI. So the way that I'm defining the group of pure automorphisms, I'm going to drop this decoration, but you have to remember that it is part of the definition. But the way that I'm defining it, I have a surjective map from this group to a pure mapping class group, and the pi G comma n of so the pi G comma n from the representation variety. The character variety is equivariant under this action. It's equivariant. So meaning I can first apply the automorphism over here. So how does the automorphism act here? So I didn't say this. So let me tell you what are the actions. So this guy acts on this side, and this guy acts on this side. So let's say what the actions are. So the automorphisms we can understand rather easier, and then you can take it as a definition of the action and the character variety to make it equivariant. So what is the action? If I give you an automorphism of the domain, then if I give you a homomorphism from this group, that's why I call it domain, to any other group, in this case SL2R, then I can precompose it and I get another homomorphism from this domain to SL2R. So then I have this IG comma n, then theta tilde here, and this goes to SL2R. So if I combine them, this becomes another element inside this. And that means that I'm giving you an action of the full automorphisms of this group on the representation variety. And you see that it is canonical on the ring R. So it doesn't matter, so it is kind of functorial on the ring R. So that's why it is an action on the scheme. So it acts on that. And then you can, in fact, define the action here and that to be in a way that makes it equivariant. You can also make it more concrete by saying that if I give you theta is any outer automorphism of this, in order to define the action, I have to tell you what it does to the coordinate functions, and then you simply apply theta to gamma and realize that because these are class functions, then it doesn't matter what theta does to this. So you simply define this to be what theta does to gamma. And then this satisfies the pre-K relation, so you can extend it to the full scheme. And these are compatible with each other, therefore we get that equivariant map. So my goal is to understand the orbits of this action. So we want to understand the orbits of this action on the character variety. And as always, whenever you want to understand an orbit, the first question is what are the conservation laws? So you first try to understand what are the things that are always invariant under the action.
Why did they need all this story? I mean, gamma GN acts on the then twist somehow, and that gives me an action.
Gamma GN is generated by then twists. So that one acts on what?
No, but gamma GN acts on the simple curves.
Gamma GN acts on the simple curves, that's correct.
And that gives me presumably some action on the character variety. That's not.
But the character variety is not just about simple curves. First and second, I have to tell you at the end when I want to give you an algebraic action, I have to tell you what it does to the coordinates. And that is what I'm doing to the coordinates. Right? Did I answer?
Non-linear polynomial action.
It's a polynomial action. I am giving you exactly what you are doing to the coordinates. Okay, so now in order to understand the orbits, first we ask what are the things that are invariant under the action, and then we say within these restrictions, do we get as chaotic as possible? So some of the things that are invariant are what? So for instance, if my image is absolutely reducible, it will be still absolutely reducible. So definitely this thing is invariant under the action. If there is a concept of if I work on the automorphisms and the rep part, maybe it's rather easier to see. So for instance, if I can define a concept of Zariski closure for the image, and then if it is Zariski dense inside SL2, it will remain Zariski dense, because at the end of the day, I'm precomposing. I'm not kind of changing the image of my representation. So if there is a concept, and I will define, we define such a thing as a Zariski open of this, which kind of captures the Zariski density of my representation. So we define, we show existence of a open subscheme that we refer to as sufficiently Zariski dense. It is invariant under the action. So and in fact, we show that this can be captured already at the level of traces. So there is always this pi going from this way to this way. And the Zariski density can already be sufficiently Zariski density already can be captured here. But what more? So one of the things that I have mentioned is that the conjugacy class of the orbit, the boundaries are always constant. So in particular, the traces of CIs are always constants, first. Second, if they are central, they are always central, no matter what lift you pick. So again, if I pick a point here, there is no canonical representation attached to it. No matter what representation gives you those traces, whether or not being inside the center stays the same, because all of them are the same up to conjugation in possibly some larger range. So that concept doesn't change. So this means, what am I saying? I'm saying that there are these functions. One of them is what I refer to as the essential boundary at a point. So let's say n is a function from this. Okay, there are too many n's. But this is a function, so you will see it. So two non-negative integers. So what is it? I give you a point here. So let's say if x is in here, then n of x tells me how many of these boundary guys are not going to the center. I get to my proofs, to my results.
I think you better stay.
You felt like a few minutes late, so.
So n of x is the number of boundary guys that are not going to, so rho of x is not plus minus 1. So this number is, in fact, the guys that are not going is invariant, is fixed, and they are invariant under the action of the mapping class group. So if I apply this, it stays the same. And the other thing is the traces of the boundaries. So inside these ones, for the essential boundary, I need to only keep track of the traces. So let's say k going from this to a to the n, it keeps tracks of the traces. So k of a point just tells me what are the traces at this point.
You only care about the C's, not the A's and the B's, only the C's?
Only the C's are fixed under the action. The A's and B's are getting crazy, right? But these are fixed under my action. So I have to fix them and then hope for any kind of density.
So in some other literature, like it's called the relative character.
Yeah, so fixing this is called relative character variety. But now I also point out that sending something to plus minus 1 is also invariant after this. So I modify the relative character variety and I say, okay, so these boundary curves are supposed to go to 1 or negative 1 as a matrix, and the other ones I'm fixing the traces. So this way I'm going to define, put it over here. So this way I'm going to define what's called the modified relative character variety. So modified relative character variety. So I have the previous decorations. Now to a subset of this, I'm assigning some signs. To another subset, I'm assigning traces. So this is the traces in the essential part, and this is the signs in the rest that are supposed to go to plus minus 1. So this is invariant under my action, and that is where I can only hope for density. Now here are the results that we prove. The density results, so at the level of the Zariski. So we show that there are two exceptional cases. So one family for genus 1 and one family for genus 2. And now I don't have the time, so just say we show there are two exceptional cases that we parameterize completely and say what they are. And what we say is that if you start with a point inside the character variety, the sufficiently Zariski open guide, if F is a characteristic zero field, and X is not among these exceptional ones, and the orbit is infinite, then the orbit is dense. The Zariski closure of the orbit is exactly what the modified relative character variety gives us. And then we have the Archimedean version of this, which answers the question by Goldman. So the Archimedean version, it says that again, this time you start with X coming from, so if I give you rho from I G comma N to SU to C with dense image. if X, the bracket row, is not one of the exceptional ones. So for instance, these you can drop if G is not 1 or 2, but or some other restrictions. These are quite concrete. And the orbit is infinite. This condition you can drop if G is not 0. So then this density automatically implies that the orbit is infinite. But if G is 0, the orbit can be finite. But if the orbit is infinite, then it is dense in the unitary part of the relative character variety. Is
Real topology.
in the real topology.
This is a big thing.
In the real topology, the Archimedean topology. In where it's supposed to be.
Minimal.
And we have the p-adic version. The p-adic version have two versions. So version 1, it says that if I start with X inside the character, right? It's the same type of statement, this time in p-adic topology. And one comment is that if I give you this means in the p-adic topology, the representation is dense. It's kind of like the SU2, SL2ZP, where the row has a dense image. So then with the same conditions implies, but this time is not going, I'm not going to give you density. I'm just going to tell you that this closure is open in its where it's supposed to be. In fact, our proof gives open in both of these, but then there is a result by Goldman and Xia that says that there exists a measure where your action is ergodic. So when you have an open subset, it's already everything. So then combined with that, we get this. But here I do not. So that's the last version, and then I stop. And so I was interested in finitely many orbits, stability, mod p to the k results. But for that, one has to be careful. So this n that I mentioned here is actually semi-continuous from the bottom. So that means that when you mod out by some ideals, you might introduce more identities in the boundaries. But if you do not introduce any identities in the boundary when you mod out by p, then I'm going to drop this h to decorate, to mention that. So there we show that the stability mod p to the k. So this thing has only finitely many orbit closures. In particular, you get a stability of the number of orbits mod p to the k as k goes to infinity. Sorry that I went off.
Questions?
In the Archimedean case, you have two values in SU to C. Can you say something if it's not compact values, but
So the Teichmuller theory itself, yeah. So sometimes your orbit is like the action of the mapping class group in the modular space.
So I think one way to answer that, if I may, is Thurston studied the action of a mapping class group, but he had to go to the boundary, and this is the theory of measured laminations, because if you want to get ergodic theory, you've got to make something compact if you act discretely in the Teichmuller space. So he goes to the boundary. The beauty of the p-adics is that the p-adic integral points are already preserved under this action. There's an integrality here that's completely new and preserved. So that you have this automatic compact topological space on which you have the action of a mapping class group. And now it seems to be acting with minimally.
But again, you can also go the other way in the p-adic. So you can replace ZP with QP
Then you
and
start.
ask Whether or not you have a Teichmuller theory there, I don't know.
Yeah,
It's a good question.
Right, but there's already this fundamentally new invariant set, which in the real case, you have to run to this compact component of Goldman. And all the other components, Goldman has some very non-wandering, I mean, of course, he's got some action, which is ergodic, but the beauty, at least periodically, is that the integral points are preserved. So these polynomial maps preserve integers, which is why they're of interest to someone like me.
The one thing that I didn't get to mention was, so when G is 1 and N is 1, I have pointed out that you have this one puncture. Torus. So then the boundary becomes the commutator. So that means you are interested in this one and fixing this. But I wrote the computation that this becomes the trace of A squared plus trace of B squared plus trace of AV squared minus trace of A, trace of B, trace of AB, and then minus 2. So now you get this equation over here. So if you fix K to be -2, you get Markov triples. So that's the connection between, so for instance, for the integer one, that is what Markov was interested, what are the integer solutions of this? And then, in fact, that's the connection between the length of the simple curves in the moduli surface. Because he was interested in these triples because of the connection to approximating irrational numbers by Diophantine properties and what are the worst cases. And that's how you can realize them as lengths of simple curves in the moduli surface.
From a Diophantine point of view, all these relative character varieties are log Calabi-Yaus, on which you can ask about integral points, and they don't fall into Voigt's conjectures because they can be infinitely many. And what's interesting here is the mapping class group seems to act on the integral points, or does in certain cases, with finitely orbits. So you have a sort of non-linear setting where you have the group doing all the work for you. So it's a very rich set of log Calabi-Yaus.